Good morning. Third day of the Merano Wine Festival Digital. We have Sunday, 8th of November. And now we have a particular presentation in cooperation with Ives and Eno1. Thanks for this cooperation. We have with us Alexander D. Levin from the Oregon State University. Also, grüß Gott zu diesem dritten Tag des Merano Wine Festival Digital. Wir haben heute im Rahmen von Wine Innovation auch wiederum eine Präsentation mit einem besonderen Thema. Dank Alexander D. Levin von Oregon State Universität. Das ist im Rahmen eben, wie gesagt, Wine Innovation in Zusammenarbeit mit Ives und Eno1. Danke. Buongiorno a questa terza giornata, è domenica 8 novembre. All'interno di Wine Innovation, grazie alla collaborazione di Ives e Eno1, abbiamo una presentazione molto particolare insieme con Alexandre D. Levin della Oregon State University. Il tema è Does Water Deficit Negatively Impact Wine Grape Yield Over the Long Term? Il deficit idrico ha un impatto negativo sulla resa del raccolto a lungo termine? Grazie e vi invito a seguire questa presentazione e grazie a tutti.
Okay, welcome everyone. Thank you so much for joining me, and I just wanted to extend a sincere thank you to the organizers of this meeting and for asking me to come and speak. Of course, it would have been nice to have joined everyone in Europe, but of course this year is unlike any other. So the title of the talk, as you see, is Does Water Deficit Negatively Impact Wine Grape Yield Over the Long Term? And this is something that I've been working on since my PhD, and I was thankful to be able to put this together with Alan Deloire and Greg Gambetta, and I believe Alan will be talking tomorrow about grapeberry growth. So without further ado, so first I wanted to just start with a brief background about who it is that I am and why I exist, because I'm pretty sure most of you don't know who I am. Following that, we'll review a little bit about grapevine yield formation, because of course it's important to understand how yield is made by the grapevine before we can understand how water deficits might negatively impact that. We'll go over a little bit about how current season water deficits impact grapevine physiology and growth. And finally, we'll talk a little bit about some work that I've done looking into whether or not long-term water deficits negatively impact grapevine growth. Who am I and why do I exist? Well, I'm a viticulturist, and I'm also the Viticulture Research and Extension Program Leader at the Southern Oregon Research and Extension Center with Oregon State University. I'm an assistant professor in the Department of Horticulture at OSU, and I'm also a core faculty member at the Oregon Wine Research Institute, which is an interdepartmental institute at the university that consists of various researchers in the fields of viticulture, plant pathology, pest management, enology, chemistry, wine sensory, and economics. Before that, I got my PhD at UC Davis in horticulture and agronomy, and my areas of expertise are, broadly speaking, are plant-water relations, plant ecophysiology, and vineyard irrigation management. So before we can understand or answer the titular question of whether or not water deficits negatively impact grape yield in the long term, we really have to first understand how yield is formed in the grapevine. And then after that, we can talk a little bit about how water deficits at various developmental time periods impact that growth and physiology. So grapevine yield is the ultimate product of many yield components that are formed over the course of 2 consecutive growing seasons. Accordingly, they're subject to manipulation by both the grower and the environment. And of course, the grower can alter the environment in some sort of way through various cultural practices. The simplest 2 factors that determine vine yield are clusters per vine and cluster mass. The number of clusters per vine itself is a product of the number of buds left at pruning and the fruitfulness of those buds. So grapevine buds are actually compound buds. And they consist typically of 3 buds inside of each individual, what's called a latent bud, the bud that you leave at pruning. Now, not all of these buds burst evenly at the beginning of the season. Some buds will push more than one shoot, while others may not push at all. And we do often see this in cane prune systems. And so here I tried to find a picture of a cane here just after bud break, and what we can see here is closer to the trunk on the left, some stronger growing shoots, some buds that pushed more than one. As you move towards the middle, a little bit weaker bud break, and actually if you can see there, there's actually a bud that did not push. And then as you head further out towards the tip of the cane, you'll see stronger shoots being pushed. In any case, bud number and the shoot number, after the grower conducts some sort of shoot thinning to adjust for density, are both determined by the grower largely, just prior to and within the growing season, respectively. However, the fertility or the fruitfulness of those buds is set in the season prior, the one before pruning. So here we can see bud fruitfulness in the figure on the left. And this is measured under a microscope, and the data here are the percent of dissected buds with clusters. So basically the buds are dissected, you look to see if there are any clusters in the bud, and that's it. Simple presence or absence measurement. And what we can see here is we can see that around bloom time, there's very low numbers. The buds are not developed yet. However, as the year progresses, those buds become more and more fruitful, more and more of them have clusters, and they typically reach their maximum fertility or maximum fruitfulness right around harvest, although I should point out that most of the clusters are there around veraison. So basically from bloom to veraison is the time where most of the development is occurring. Now I do want to note that I'm using the term cluster here, although of course it's not a cluster yet, it's in the bud. We really should be calling it an inflorescence. So cluster mass itself is the product of berry mass and berries per cluster. Berries grow and develop over the course of one season. They're fertilized in the spring, or the flowers are fertilized in the spring, and then the berries grow and develop and are harvested in the fall. So berry mass at harvest is itself a function of any grower cultural practices and or environmental conditions that occur only from that period from fruit set going through to harvest. And as I mentioned earlier, Alan's going to be talking about berry growth and development, I believe tomorrow, so I won't go into too much detail about that. But you can see here that berries have these two distinct growing periods. We have the pre-veraison period where they grow quite a bit and then slow down as they enter lag phase. And then once they complete veraison, they grow rapidly again before they reach their final size and then are harvested later. And these 3 curves are just 3 different irrigation treatments that were applied to these berries. I'll talk about that in a little bit. Finally, the number of berries per cluster is the product of the number of flowers per inflorescence and the percent of those flowers that set berries. And you can see that here. You can have very high berry set, or you can have very low berry set, or you can have lots of flowers per inflorescence or very few flowers per inflorescence. Now, like berry mass, the percent berry set is a result of only current season cultural practices and environmental conditions. And in fact, it's quite sensitive to environmental conditions. For example, berry set is typically increased under warm and dry conditions that would encourage the growth of the pollen tube down in towards the ovary and to fertilize the egg. Conversely, this growth is greatly decreased under cool and wet conditions. And very often, in fact, we had this happen this year in 2020 in Oregon. We had some odd cool and wet conditions around berry set, which was somewhat unusual for us, and it resulted in greatly reduced berry set. Now, some of the early flowering varieties that we had escaped this, and they had a very good berry set, but some of the later flowering varieties ran right into these cool and wet conditions, and unfortunately their berry set was greatly reduced. Of course, because you can't make a flower without first making an inflorescence, flowers are necessarily differentiated after inflorescences, and this typically occurs around bud break, the year of harvest. Now, if you remember just a few slides ago, I pointed out that the inflorescences themselves are developed in the latent bud following bloom and typically reach maximum development around veraison and maybe a little bit after veraison. And then so as you enter harvest of that first year, the inflorescences themselves are not quite developed into flowers just yet. They exist, but they don't have any flowers on them. I love to show these micrographs. These are quite old. In fact, I believe they're older than I am. These are some of the first scanning electron micrographs of the development of grapevine inflorescences. On the very far left, you can see basically what that is that's the main axis of the rachis itself, and developing off of that main axis in the bracts, which are designated by BR there, you can see the branch primordia designated by BP, and those are the branching points of the inflorescence that branch off of that main axis. In the center panel, you can see slightly further along in development, a more developed inflorescence with a little bit more development in those branch primordia. And then on the very far right, this micrograph was taken right around bud break, a much larger zoom on this micrograph, and you can see that flower initial, Fi, that the arrow points to. That is what will become a group of flowers. And as you can see, as is typical for grapevine, they're in groups of 3 or 5. In this case, there are 5 of them. So when you consider the overall course of yield formation and all the yield components that make up grapevine yield, you can kind of group them into these developmental times that occur over these 2 seasons. Now, clusters per vine, again, you have to make an inflorescence first. So the very first thing that happens in bloom, or just starting after bloom or flowering in the first year, is the development of the inflorescence. And then you have differentiation of the inflorescence into flowers, which occurs sometime in between harvest of the first year and just through and after bud break of the second year. Once that happens, the inflorescence continues to grow and then flowers. So you have berry set occurring in year 2. Whether or not those berries set determines the number of berries per cluster. And I've designated that berries per cluster is a year 1 to 2 sort of developmental time. And that's simply because it is such a strong function of the number of flowers that are present in the inflorescence. Once berries are set, you have a berry. And it's really just subjected to that year 2 conditions, the current season. So anything that the grower would do in that current season, anything that happens in the environment, heat, rain, cold, drought, all of those things impact berry development and a resulted berry mass. The number of berries per cluster and the cluster mass, or excuse me, the number of berries per cluster and the berry mass yield the cluster mass, which and then multiplied by the clusters per vine give you the vine yield. So water deficits, water stress to the grapevine at any of these developmental time points can have various degrees of impact. Okay, so let's take a look at how water deficits in the current season might impact the growth and development of the grapevine and how those are related to long-term productivity. Well, one of the first things that happens when the grapevine starts growing is, of course, bud break in the spring. And if you have dry winters and or a dry spring, there can be some negative impacts. Here I'm showing on the left-hand side some weather data or climate data from our region in Southern Oregon, and you'll see the thick black line representing a 30-year average of accumulated rainfall over the water year. Now, the United States Geological Survey defines the water year as the period of time from the 1st of October until the 30th of September. And that's the time, at least here on the West Coast, where we get most of our rainfall. So you can see the 30-year average increases quite rapidly, particularly in the months of November, December, and January here in the Northern Hemisphere. And then eventually the rainfall slows down as we enter the springtime, and into the summer we don't get very much rain at all, typical of a Mediterranean climate. And our yearly average rainfall is about 500 millimeters. And what you can see there below that thick line is the curve representing what we got in the 2020 water year, which would have started on the 1st of October in 2019 and then finished just this past September 30th. And we were quite low, actually just about 300 millimeters of rainfall. And we were very behind by the time a bud break came around. And you can see here on the right, we had a lot of reports of uneven bud break and poor development of shoots early in the season. So that would be the first thing that would negatively impact yield going forward. As the season progresses, if you continue to experience water deficits, one of the next things that you're likely to see is a reduction in the elongation of the shoots. Here on the left, you're seeing some data that were collected some time ago, published in 2010, of various irrigation treatments that were applied to grapevines and shoot length measured over time. So of course they all start out the same at bud break, but then the squares with the little dot in there are receiving very little water, whereas the squares that are filled or have a large dot in them are receiving quite a bit of water. And you can see how responsive shoot growth is to water availability in the soil. So the shoots slow down, and what happens then? So when typically there's a lot of water available, the shoots grow and they photosynthesize and produce a lot of carbohydrates, which are then utilized to grow more shoots, of course. But as the grapevine experiences some level of water deficits, the amount of carbohydrates that are allocated to continued shoot growth and development are subsequently reallocated to feed more growth and development into the roots. And this is sort of the plant's ecological adaptation. Of course, when the soil is drier, the plant decides to send, or not decides, it responds by sending more carbohydrates to the roots to presumably search for more water in the soil. So after growth is reduced slightly or reallocated with respect to carbohydrates, the next step when grapevines experience water deficit is the closure of the stomata. And now the closure of the stomata is simply the plant's active response to control water loss out of the leaves. And what essentially happens is that you start to reduce the water loss, you reduce that gas exchange, and you impact photosynthesis negatively as well. Now, one interesting thing to point out here shown in the figure is that the photosynthetic rate, although it does go down with decreasing stomatal conductance, which is shown on the horizontal axis, it's not a straight line. And so photosynthesis is a little bit more resilient in the face of water deficits than is stomatal conductance. But once you get to that kind of break point at 0.2, then the photosynthetic rate drops dramatically as the water deficit becomes quite severe. Finally, when you can't do anything in the leaf to change how it's growing or how the water is being lost, all of a sudden the leaf is experiencing all this solar radiation and energy that it can't do anything with. So the last step is to essentially change the orientation of the leaf with respect to the sun, or to lose the leaf and drop it off of the grapevine. On the left-hand side, you can see the response of the leaf angle to increasing water deficit. And surprise, surprise, when plants get dry, they wilt. And this is just a graphical interpretation of the leaf wilting, or the leaf angle changing and becoming more vertical. On the right-hand side, you'll see that as the water deficit becomes more severe, what you start to see is the leaf abscission, and the leaves are they dry up and they fall off of the vine. With respect to the fruit, As I mentioned earlier, the berry has these distinct growing periods, a pre-veraison period and a post-veraison period, and it exhibits over the course of the whole season this double sigmoidal growth habit, which is typical. Now here we have 3 different irrigation treatments. The open circles in the very middle there receive the same amount of water over the course of the growing season. The filled circles at the bottom received a severe water deficit early, before veraison, and you can see that that significantly reduced the growth of the fruit. Even when we reapplied water at the end of after veraison, the berries grew again, but they never caught up to the original berry size in the control berries. They also had a delayed harvest. Now with the post-veraison water deficits, the berries did shrivel a little bit towards the end of the season as we approached harvest, but most of that growth was made earlier in the season. So you can see the impact of the pre-veraison deficits being much more significant than the post-veraison water deficits. At the same time that all of this is going on above ground with respect to the shoots and the leaves and the berries, there's a lot going on within the trunk and the roots, and the storage reserves of carbohydrates are constantly being replenished and refilled and used. Particularly in the spring, the storage reserves are at their highest, and they're remobilized to support that early season shoot growth. So you can see after bud break, the storage reserves are depleted quite rapidly until we get to a bottom, the lowest point there around flowering, at which point the storage reserves are at their minimum. And then at the same time as the vine is growing the berries and concerned with reproduction on that level, it is also concerned with surviving another winter. So it's replenishing the storage reserves at the same time. And those storage reserves that it's replenishing will support shoot growth the following year. So ultimately, when you experience water deficits in the current season, you change the canopy architecture, you change the amount of leaf area, you change the whole vine photosynthetic capacity and the whole vine ability to produce carbohydrates, whether they be used to support the current season's shoot growth, the current season's berry growth and berry ripening, or the current season's storage of carbohydrate reserves, which will ultimately be used to support long-term productivity. So it's important to understand that the current season water deficits really can have a lasting impact on long-term productivity. Now, what about water deficits over the long term? So we had a study where we had 3 irrigation treatments that either stressed the vine's early season, meaning pre-veraison from fruit set to veraison, or later in the season from veraison to harvest compared to a control. And we measured yield components over many, many years. And here are some data showing you a comparison between yield and berry mass. Now, yield turned out to be a very strong function of berry mass, and you can see that illustrated here. Now, the 3 curves are the 3 irrigation treatments in both figures. If you would just ignore for a second the 2016 data, I'll talk about that in a moment, but you can see that the early deficits really reduced berry size. As I said, pre-veraison water deficits significantly reduced berry size from 2012 to 2015, and that correlated with a very strong reduction in yield. In 2015, we did see strong reductions in berry size due to the late deficits as well, and that also reduced yield somewhat, but not nearly as much as the early deficits. Now in 2016, we said, hey, we're done with doing the same experiment over and over again, so we watered all of the vines the same amount to see how they would respond to then having being well watered after years of being stressed at various times. And you can see that with respect to berry mass, all of them had about the same berry mass. And this was very interesting, but sort of correlated with what we thought, that berry mass is really just going to be a function of that current season's conditions, and indeed was. However, when we look deeper into clusters per vine and berries per cluster, we saw that if you look at clusters per vine measured here over the 4-year period, it was always lower with the early deficits as opposed to the late deficits where there were no effects on the number of clusters per vine. So when we stressed the vines after veraison, the number of clusters per vine the following year was the same as if they weren't stressed in that time period. However, if they were stressed before veraison and experienced significant water deficit before veraison, then we saw less clusters the following year. On the other hand, when we look at berries per cluster, we really didn't see a consistent effect of anything at all. Now, of course, these curves change over time. This is a vintage effect, of course. When we see everything is, fairly high numbers of clusters per vine and berries per cluster in 2013, and then they drop over time. That was essentially a vintage effect there. But what we didn't see was the response of berries per cluster to any of the irrigation treatments whatsoever. And this is illustrated here. If you look on the left-hand side, what we're showing is the number of clusters per vine in year 2 as a function of the average pre-veraison water status in year 1. So we measured the water potential at midday at regular intervals, and these data are averaged across 5 years and 15 cultivars. We saw some differences between cultivars, but they were remarkably similar, which was quite surprising. So what we see here is that when we have the early deficits, pre-veraison water deficits in year 1, we saw a significant reduction in clusters per vine in year 2. Now remember, that period of time between bloom and veraison is when most of that bud development is going on. And so here we have a situation in which we had a water deficit during that time, and we saw less clusters the following year. At the same time, we did not see any impact on on berries per cluster with early or late deficits, which was very, very interesting considering that we had significant late deficits and dry winters, but the number of berries per cluster did not change, and we also didn't see any effects on berry set. So we interpreted that as berries per cluster just really wasn't that sensitive to water deficits. Ultimately, we summarized the relative sensitivity of these 3 main yield components in this figure here. And what we're showing is berry weight, clusters per vine, and berries per cluster in 4 years. And the difference, the relative difference from the control for each of the 2 irrigation treatments that were different from the control, the early deficit treatment and the late deficit treatment. And as you can see, berry fresh weight was the most sensitive of the 3 yield components to water deficits because of the fact that berries grow in that one season. And they were very sensitive to early deficits compared to late deficits. Next, clusters per vine was the next most sensitive yield component to water deficits, again with most of the sensitivity due to early water deficits and with essentially no sensitivity to late water deficits. And finally, there was very little sensitivity of berries per cluster to water deficits at either time of the year. So what does this all mean? Well, it means that the timing is everything. When you experience the water deficit has various impacts on grapevine growth and development with various implications for long-term productivity. If you experience water deficit very early in the season, which is quite rare unless you're in a very arid growing condition, you'll have decreased shoot growth and potentially decreased fruit set and reducing the number of berries per cluster. If you have water deficits from veraison to harvest, from fruit set to veraison, you'll not only reduce the berry size in the current year, but you'll reduce the bud fertility or fruitfulness for the following year. And if you have water deficits from veraison to harvest, you might slightly reduce the berry size, giving you a lower yield at the end. So all of this can be mitigated with irrigation if you're able to do so. With respect to management of these problems, it would be prudent to make sure that you do not have a water deficit from bud break to fruit set so that you can develop a healthy canopy to provide yourself with enough leaf area to ripen the fruit appropriately. From fruit set to veraison, you can impose a slight water deficit if you'd like to control berry size, but keeping the water status of the vine above minus 1.3 megapascals of midday leaf water potential would be fine, and you would not reduce yield the following year. Otherwise, you might have a lower cluster number the following year. Finally, I do want to thank all of the people that have allowed me to do what I do, my great lab, my collaborators' labs in the Southern Oregon Research and Extension Center, my colleagues on campus at the Oregon Wine Research Institute, and all of our sponsoring agencies. Can't do it without any of them, of course. So thank you for your attention. And if you'd like to get a hold of me, my email address is listed there. You can also message me on Twitter @AlecLevin, or you can follow my lab on Instagram @LevinLab.